Michael, please go ahead and talk to us about Harmonic.
Thank you. Thank you very much. I'm truly honored to be invited for this. I would invite anybody who has questions and stuff. I mean, I tried to keep this reasonably short. So if you have questions or comments as we go along, I think it'd be fair game to just, have a little discussion around it. I am going to talk a little bit about business here and broadcast business. So I just want to make it clear that the technology stuff I talk about is Harmonic. The business stuff that I talk about is really mostly my own opinions. So, but I'm still happy to discuss it. So really the topic that I'm interested in tonight is, why do we worry about ATSC1 when, ATSC3 is really what everybody's thinking about? So first of all, let me touch on, sort of what I see as the two key ATSC1 components for the ATSC3 transition. The first is, and of course we're in the midst of the era of the lighthouse. So the lighthouse is how we have to launch ATSC3 because the FCC doesn't have extra channels to give to everyone this time around. So and the lighthouse means that people, stations, some station will give up their ATSC1 in order to transmit, a number of other ATSC3 signals.
We need to mute, please.
Yeah, I'm just trying to find out where it's coming from. Here we go.
But so that means that most of the other stations in the market have to take on at least one more channel, sometimes more than one. And that's pretty straightforward and pretty well within the capabilities of current encoders. Toward the end of the transition, we're going to get into the nightlight era, which is really the opposite of that. So, at some point, if everything works the way it's supposed to, ATSC3 becomes in and of itself a really good business model, and stations want to leave the lighthouse and turn their own transmitter over to ATSC3. But of course, that's not necessarily, they're not necessarily going to want to give up their ATSC1 transmissions at that time. So just looking at it, for the lighthouse era, the stations, send their, I got, this is reversed here. Somehow I missed one of the slides. Okay, anyway. So this is the nightlight era where ATSC3 stations send signals back to nightlight stations, and the nightlight stations then, of course, get carried on ATSC3 on other stations. So, this is an era sort of after the crossover when stations are making money on 3. But they need to keep their ATSC1 alive for a while. I really think it's going to be a commercial decision. The FCC has mandated a 5-year period, but I don't think 5 years is going to be anywhere near enough for most stations from a commercial point of view. So looking at this, the conversion from analog to ATSC1 took about 11 years. But that 11 years was actually really accelerated. The FCC had several mandates. They mandated tuners in the TVs. They subsidized set-top boxes for people at home so that they didn't have to buy a new TV. They actually mandated turning off analog. And they gave every TV station in the country a second channel. So these were all great accelerators to the transition from analog to ATSC1. So in terms of the thinking about the timing, according to what I've seen, a TV set in the US usually lasts about 7 years before people replace it. Households supposedly have an average of 2.3 TVs. You can buy a 3.0 TV now, but you're not going to go to Best Buy and find one. And manufacturers usually take about 3 years from when they decide to create a TV model until you can see it in the stores pretty widely. So, looking at the numbers, I wouldn't think that we're going to see 70, 90 to 90% penetration of 3.0 TVs in households much before, the probably the middle of the 2030s. So it's going to take a while to get that sort of penetration. Um, and then eventually, especially the primary stations are going to want to leave the lighthouse. They probably will have, a lot more programming that can only be really transmitted with quality in ATSC3, like ultra high definition, wide dynamic range, all those sorts of things. Um, so, if you look at it, if ATSC3 is successful, it's probably going to be because stations see, increased revenue, and or there's some killer app that sort of drives the public towards it faster. I think this transition from, the ATSC1 to the ATSC3 business model is what it really is. Begins sort of around when the TVs are maybe have a 70% penetration. And, it's sort of, the majority of stations will probably be somewhat transitioned by the time you get maybe 90 or 95% of TVs. But, until you get, well into the 90s of penetrations, I don't think most stations are going to want to disenfranchise viewers. So that's going to create the need for night lights. ATSC1 is critical, particularly in those middle and late stages, because the channel density is going to have to increase even beyond what it is today.
It's fine. Okay, thank you.
So, the value of ATSC1 is actually very high. It's, I read $100 billion, number for 10 years. That may be low, that may be high, I'm not sure. But ATSC1 encoders are going to have to continue getting better because ultimately with the night lights, you're going to have to fit a lot of TV stations. This is not a typical one-to-one channel share. This is more like trying to fit, 4 or 5 TV stations maybe on a pair, or maybe six or 7 TV stations even on a pair of transmitters. It's possible to get much better performance out of MPEG-2, or relatively much better performance, but it's very expensive. MPEG-2 is a 37-year-old standard. And right now, we're sort of about 5 or 10 times the performance that was originally anticipated for MPEG-2. So it's not easy to get there. So looking at the phases, we've got phase 1 that we're in now, the lighthouses. Phase 2, people outgrow the lighthouses, and nobody really knows what applications are going to drive that. Certainly, ultra high definition for sports is going to be a candidate. Paid programming may be likely. I mean, the capabilities are all there for that. The channel density will increase relative to ATSC1, so there's opportunity to make more money with more channels. But stage 2 may be limited by the ability to find enough ATSC1 spectrum to keep everybody on air with ATSC1. And then finally, in the nightlight phase, you'd have stations, wanting to change to 3, but there's still quite a few ATSC1 only households. Nightlight stations, will take on ATSC1 carriage for other stations, and also to feed legacy cable. That it's, if you look at which cable companies you feed, most TV stations have 1 or 2 primary cable companies, but they very often have a large number of, what we call mom and pop cables that are likely to still be doing, QAM, even in another decade. So again, the ATSC1 performance is going to be critical. So let me just go through a little bit of history. I joined actually Divicom in 1998. So these are all phases that I actually lived through and, installed equipment and knew how it operated and all that. The first generation of encoders starting in around 1997, now I'm talking about HD encoders, were what I called, and I think people commonly called, the six-pack, which is a sort of a window pane arrangement, usually of six window panes. Manufacturers would take, half a dozen either SD, actually in some cases they were actually chassis, in other cases they were cards. They tie them together, usually with maybe an encoder ahead of it to slice up the picture. And there were a lot of disadvantages to this, but it was a expeditious way to create early HD encoders. Some of the problems were that you didn't really have any motion search across the mullions. I mean, there was maybe a little bit just to sort of smooth things out. You didn't really have much communications between the windows. So, if the football's flying across and it crosses a mullion, it's a surprise to the next encoder when it gets there. The mullions show up if you get a camera pan or that sort of thing, the things that break up encoders now. So there was really poor efficiency, especially when things are happening across the whole frame. To my knowledge, I don't think any of those encoders had look ahead. That they very often had a fixed GOP. There wasn't a lot of horsepower there for programming. So these were ASIC-based encoders. The ASICs in those days did have programmable cores, but there wasn't a lot of horsepower available in those. These encoders, a lot of these encoders were built around a chipset made by IBM. And, finally, in those days, if you changed chipsets, you lost most of your R&D. You had to go back and sort of recreate what you'd done on a new platform. So just a little later than that, Divicom came out with their first HD encoder, a little bit later than most of the six-pack encoders. And that encoder, that was the MV400, was a slice encoder. So basically what happened was each chip, each ASIC, did a slice of the picture rather than breaking it up into panes. Those ASICs had the capability of talking to each other over a bus. So you had motion search and coordination from across adjacent stripes or slices. So you could do a little bit better filtering because you had access to the entire video line. They were much better at being able to do an adaptive GOP because again, you had, more of sort of like the whole horizontal structure available. Since you used more of these ASIC chips, you had more programmable cycles available because they were spread across more CPUs. There was, in the early days, some FPGA enhancement in some of these encoders. The efficiency was significantly better than a six-pack encoder, but they didn't have look ahead. They were single pass. Later on, the MV500 had sort of a quasi look ahead, but they were really basically single pass encoders. They had, usable statistical multiplex performance, but it wasn't great. These were usually based on the C-Cube chipset. C-Cube was the parent company in those days to Divicom. So we had it, but a number of our competitors used that chipset as well. But again, when you change chips, you lost a lot of your R&D, and so you had to invest again in a lot of engineering. So just looking at the same era, the SD encoders were actually much more advanced. So in that era, around the same time, around 1998, were encoders like the MV40 and 45. Now these were single slice encoders, meaning the picture was not split up. A single chip did the entire picture. So the motion search range was was limited really only by the speed of the chip. At least the Divicom encoders used cascaded ASICs. So they had enough chips to actually encode the picture 3 times. They actually encoded it twice, once for look ahead and once for the final picture. The third chip was used actually for filtering. So these were the first encoders to have motion compensated filtering, at least the first that I know of. The GOP was very adaptable, and the look ahead made GOP adaptation a much more powerful tool. They had some picture recognition features. I'm going to talk about that a little later on, but picture recognition features are the encoder, particularly the look ahead portion of the encoder, finding things in the picture that you want to do differently. So if you detect a logo or you detect a lower third, some of those things were pretty common in the early days. You could use either different rate control or even maybe some modifications to the algorithms to get better performance around those picture elements, which people look at, and they're sensitive to the artifacts that surround them. That again, they were full 2-pass, so the statistical multiplexing was really much better. And essentially, they had most of the features that you associate with modern encoding. So a lot of the things that I'm going to talk about in software later actually appeared in this generation of encoding. But again, the disadvantage was every time you got a new chip, you sort of threw away a lot of R&D and started over again. And a lot of that R&D was hardware. I mean, there were probably as many engineers doing hardware design as there were doing software design or firmware design. Which brings us then to the third generation. So this is one, there's probably quite a, well, there's still a lot of these encoders still in use, the Electra 8000, 9000, the Thomson EM4000. So these are these are single slice for HD. So these were the first chipsets that did HD in a single slice. Typically, they did either AVC or MPEG-2. And that's one of the keys to it, is since they were designed to be able to do AVC, they had a lot more horsepower than an MPEG-2 only encoder, which actually gave a lot of tools that you could use for MPEG-2 that the engineers didn't have before. These were triple pass encoders with dual look ahead. So, when you're deciding in the encoder, so the picture comes in, and when the encoder first sees it, it has no idea what's in it. I mean, every frame can be completely different than the last one. So you don't know if there's a scene change, you don't know if it's a camera pan, you just don't know what it is. So if you do a look ahead, the first encode, that first chip, or the first encode process, can figure out what those elements are, and it can estimate how many bits are needed in the stat mux. In these encoders, then, there was a second look ahead after the filtering was applied and taking advantage of the knowledge that was gained in the first look ahead. So you got an updated estimate for the stat mux, and you also got some corrective actions for the final encode, which is the one that you actually see when you look at the output. So you could do multiple HD encodes, I mean, we just talked about 3. I think the chip actually could do about 5 MPEG-2s on a single piece of silicon. There was a lot of horsepower that was available for programming. Around the same time, this was when there was more advanced AVC. There were earlier AVC encoders, but these were, this generation were the first ones that really lived up to the standard. And the engineers found new things to do in MPEG-2 because of what they learned in AVC. So AVC, for example, has a feedback loop inside the encoder that estimates the video quality. That was to drive a deblocking filter. But some of those things found use in MPEG-2 as well, just to make better decisions about the encoding. And basically, these encoders were the greatest leap forward in efficiency of the whole era. So from the very beginning until now, this is probably the largest single leap in efficiency. So the Electra 8000 was the first encoder that I know of that did 3 HDs on a TV station. And there became a lot more types of filters that are possible. But again, like all of the previous ones, if you change chips, you got to start over on both a hardware design and on a lot of the firmware. So, again, it decreased the rate at which you can improve things. Which brings us to the current generation, the 4th generation of encoding. So really, the main thing is the old limitations don't apply. So the real limit is just how many CPU cycles do you have available, and how many ways can you figure out to make a CPU cycle, create a better picture. So, basically the improvements come from figuring out how to spend those CPU cycles to improve either the quality or the density. Now, one of the huge advantages is that the ASIC-based encoders worked because they hardwired, they had hardwiring for a lot of the basic MPEG functions. So motion search, all the things that are sort of deep under the hood were typically hardwired in those encoders. Back in 1998, that was the only way you got enough horsepower to do an encode. The disadvantage to that, though, is that you can't change those algorithms very easily. There's not much you can do. So if you want to change up how one of those fundamental functions, it's sort of like the brain stem, it's just stuff that you don't change very easily. One of the advantages in software encoding is that since you have to write all that stuff, you can change it and you can figure out how to optimize it. Disadvantages include the fact that it's really, really labor intensive to make a good software encoder. But a huge advantage is that you get continuous improvement. You're not waiting for a new ASIC to come out. And when it does, and when you do, change up generations, say in CPUs, almost all of your previous work just translates directly. I mean, in most cases, the old code will work. Maybe you can find some enhancements because the new Xeon has a couple more instructions that are useful or whatever. But you basically don't lose the work that you've made, previously. So this allows the encoder to get better continuously. And one of the things that happens is in the old days, you had the whatever it was, the MV45 and and then the MV50 came out and it was better. And then the MV100 came out and again, it was better. Now, you're not really aware that, it's continuously getting better. It may not be very much, but over time you gain efficiency. So when you go to design one of these things, there's a lot of very fundamental decisions that the engineers have to make. There is open source code. I mean, you can go download whole encoders, from a number of different sites, and it's workable code. Or you can write the whole thing from scratch, or you can buy code. You can buy off the shelf code. And then you got to decide things like, are you going to use a GPU to accelerate things? So the first thing that has to be done is the engineers, the software designers have to recreate all of those hardwired functions that were in the ASIC. And again, those were the really CPU intensive things. So a lot of them are difficult to make efficient enough to not just burn up all your CPU capacity. ASICs also had a real advantage over CPU in that when you went to C-Cube and you bought their chip, or when you went to IBM and you bought their ASIC, they came with a reference design and they came with code that made it work. So, if you wanted to build a pretty good encoder, you could basically just roll up that reference design and put some code on it, maybe do a little tweaking to fit the hardware that you put around it, and you got a pretty decent encoder. The higher end ASICs, especially the later ones, did have programmability. They usually came in two types. One was a consumer chip that was sort of mask programmed or permanently programmed, and those went into consumer goods or semi-pro cameras, that sort of thing. And then the high-end version of that chip would have like a RISC core or something like that you could program to add functions, but it wasn't anywhere near powerful enough to take over all of the chores that had to be done. So, ultimately the quality you could get out of an encoder was limited by these ASICs. And that just doesn't apply in software encoding. The quality you can achieve is really, the limitation is just how many CPU cycles are there and how good are you as an engineer or an algorithm designer. But again, it's very, very CPU intensive, and you have to write incredibly efficient code, or it just, you don't have enough cycles left to do the things that make it a really good encoder. But you can innovate on any portion of the codec. You're not limited anymore. So, if you look at open source, one of the problems is that the quality is probably limited. It was probably designed to be, a nice, handy, cheap solution to, something that doesn't require a tremendous amount of performance. It also may be designed with an architecture that really limits what you can do in the future. GPUs, there's been quite a number of GPU-based encoders out. We actually have some that use GPU cycles out of Intel chips that contain, some of those functions. But there's limitations that are actually similar to the ASIC. You have sort of a, best case that you can get out of them that is limited by the hardware acceleration that's in the GPU. So there's things that aren't easy to change. And again, you run back into this thing where if you want to change to a new generation, you're going to lose some R&D. Maybe not as much as you did with the ASICs, but you are going to lose some R&D there. So typically, the GPUs excel where you need really high density and pretty good or good encoding, but not the best quality encoding. And then that brings you to the from scratch, which is, basically you have to write everything from the ground up. You might have started with something a long time ago that you've just, replaced all the elements of over time, or maybe you just wrote it all from scratch. But it means that you can design an architecture that's easy to expand. And a good architecture allows you to keep making improvements continuously without having to go back and redesign, sort of the foundation. And again, you get back to this concept that the real job is to figure out how to use more CPU cycles in order to make a better picture. You also, in parallel to that, want to figure out how to make the code more efficient so that you do the same job with fewer CPU cycles. That one can increase the density, which makes encoder cheaper per channel, so that's a good thing. But also, as you improve the efficiency, the CPU efficiency, it frees up cycles that then you can use to increase the quality. So it's pretty common for the density to remain the same, but the quality improve. And that's because you have some of the algorithm engineers that are making it more efficient, and other algorithm engineers that are then taking those freed up cycles and using them to do a better job of encoding. So what's the secret sauce? Well, there really isn't any. A good software encoder is just really a lot of work, a huge amount of detail, and a lot of man hours. If you've got a large customer base, it helps a lot because you got to amortize all those man hours. Especially in MPEG-2, improving the sort of fundamental codec functions is pretty difficult. Most of the improvements have been known for a long time. And so really fundamental improvements in the codec itself are, they're still possible, they still do happen, but it's not where the meat of the improvements is. Again, there are things that can be done, particularly things like in-loop analysis, but that's typically not a codec improvement. That's typically an improvement in how the algorithms around the codec work. Filters and statistical multiplexing are actually very productive, but they still, you go in and, the engineers will spend 6 or 8 weeks on something and you'll get 1%. But that 1% then is cumulative. So if you if you get, 1% over 5 or 6 or 7 times in ATSC, that means you add an SD channel. Because an SD channel typically these days is 7 to 10% of the video pool. So you look for, if you can get 10%, you can add an SD channel. If you can get a little more than 10%, you can add an SD channel and maybe improve the quality of the primary channel. So those are the kind of things that you have to look for. A lot of the things that happen have been done for quite a while in non-real-time encoding. So, non-real-time encoding doesn't have the real-time limitations because you can take as much time as is practical. So a lot of the things that happen now in encoders actually have been incorporated into non-real-time encoding for a long time. So two-pass encoding, for example, has been around a very long time. A lot of the filter techniques that are CPU intensive have been around for a long time. You just couldn't do them in real time. Now there's enough horsepower to do them in real time, and with enough optimization, then you can keep a reasonable density of the encoder. So this is a real eye chart, but it's really about how do you spend CPU cycles to make the picture better. And so, fundamentally, one of the most powerful tools is to detect features of the picture, or features of the pictures of the frames. So, for example, you do rate control within the frame. So a really common one is, you find a logo. People are sensitive to the noise around the logo. So you spend a few more bits at the edge of the logo to reduce that effect. You may find that there's specific filter algorithms that work with specific kinds of pictures. So, for example, there are filters that are specific to film. Film has all that grain. It's really hard to encode. So, when you detect film, you may trigger a whole different set of filters that say, oh, I know what film is. And, oh, wow, look at all that grain. Let me take some of that away, and that makes it easier to encode. There may be enhancement algorithms. So, there may be parts of the pictures, especially when the encoder is stressed, where it's going to be a little softer than you would like, especially things like the edges of text and things like that. So you can enhance that. You can go in and you can sharpen up those edges a little bit after you've filtered out all the noise. There's what's called rate control for the overall rate control, which is assigning how many bits you're going to use per picture. And that also relates to the buffer. So you have an MPEG buffer, which is, so even a constant bit rate MPEG transport stream, the video in there is not actually constant bit rate. There's a buffer model, and the buffer is, they usually use the analogy that it's like a bucket with a hole in it. So you pour bits in the top, bits drain out the bottom. As long as the bucket is never empty or never over full, it's okay. So that's the buffer. That's the buffer in MPEG. One of the things that they've gotten really good at, though, is not just keeping a steady level in the buffer, but using the buffer to an advantage. So, for example, if the encoder sees a transition coming, the pictures are not sent in order anyway. So you can drain down that buffer so that after the transition happens, you've got more bits available. Or you can take some of the bits that would have been needed at the transition. You can move them ahead of the transition because the pictures don't have to be in order. So things like that. The StatMux bitrate request modifications. So what this amounts to is you got to figure out how many bits you need for every single video frame. And the StatMux does vary. In a good encoder, it will actually vary frame by frame, the bit rate. So if you're really smart, you can look at that picture and figure out how many bits do you really need for it to make the picture do what you want. And that's one of the things maybe I'll talk about a little bit in a minute, but the concept that you don't necessarily always want the best picture. And the reason why you might not want the best picture is you might want one of the other channels to have higher quality at the expense of the one that we're looking at now. So you may want to say, I want to keep the quality constant, and I want to keep it at a level that's appropriate to the business case or the kind of channel that I'm transmitting, in order to free up bits for the primary channel, for example. You can change the GOP. You can do in-loop feedback. So, for example, the encoder can encode a picture, look at how it came out, judge the quality, and say, oh, I can do better, and then encode it again. You can do things like that. Again, the StatMux control, you can adapt things because you've got all this look ahead. So the StatMux tells the encoder, it gives it an estimate of how many bits it's going to have. And after the second look ahead, it has a really accurate estimate. So, the encoder can look at it and can say, wow, I don't have very many bits. So what am I going to do? And so you can do all sorts of things. You can filter more. There's lots of things you can do. You can do again the quality goals. Best quality or constant quality. Or in some cases in ATSC1, I use the term best effort quality. And then there's adaptations that are specific to certain applications. So one of the things that happens for most of the earlier Divicom and harmonic encoders were designed to be, the StatMux was designed to be safe. And by safe, what I mean is, if I'm a cable company and I've got, ESPN and, Fox Sports in the same multiplex, and ESPN, is doing a camera pan, you don't want to see that in Fox Sports. And if you did, they'd be unhappy. So basically, most of the algorithms were always designed to be safe, meaning if a picture was driving the StatMux to where there weren't enough bits to go around, typically the hit would be on the channel that's creating the most complexity. And the other channels were allowed to be a little bit better quality. An aggressive StatMux will drive the pictures to equal quality. So if you've got one or two that are very, very busy, it may drive the other channels to have equal video quality, meaning they're artifacted as well. This is a difference between, a service provider who doesn't want, one of their programmers complaining that somebody else was busy and it hurt their picture quality, that sort of thing. ATSC over the air is actually different than that. In one case, you want the primary channel to never be hurt by other channels. And in other cases, you want the other channels maybe to get creamed by the primary channel even, if that's what's necessary to keep the football game looking good. So some of the things that the encoder looks for, are scene changes, logos, text, crawl. Well, these are all ones that actually have been around for a long time. Explosions, camera pans, zooms, faces, crowds, grass. I mean, there's a fellow I know in the algorithm lab that spent months figuring out how to encode grass better, because grass, oddly enough, is one of the most important picture elements because it's common to football and soccer. The floor in basketball, you want to detect that so that you're not, so you're doing the right things. Detailed, rapidly moving objects. So if the encoder's stressed and there's a football that's in the air, being passed, there's a lot of detail on it. There's the stitches, there's the pigskin, texture and all that, but it's moving pretty quickly, and you don't expect visually to be able to see all that detail. So if you got to lose detail somewhere, you lose it there. You don't want to lose it somewhere else. People's eyes, when you look at someone's face in a picture, you look at their eyes, just like you do, face to face. So, so if you can detect those eyes, you can spend bits where they're needed to make sure that those eyes look natural. You know, people on a background. So this is very common. You'll have a very busy background, maybe with motion in it, maybe somebody standing in front of a crowd. A lot of football shots are like that. So you kind of got to figure out what the person is versus what the background is, and do the right thing in both cases. People in motion, again, you know, someone's moving. If a person's moving, it's not the same as if a car is moving. You know, you don't necessarily treat it the same. So these are all the kinds of things that you can do in software, that some of these were done in the old ASIC-based encoders, but in software, you have the option of doing many, many more of them. And a lot of the improvements that we've had in MPEG-2 over the last, you know, few years, particularly the software-based encoders, are related to figuring out what's in the picture and doing a better job of that specific kind of object or picture itself. ATSC1 actually is a very unique market. So, you know, originally, you know, encoders were, well, it was an MPEG-2 encoder, you know, DirecTV bought them, EchoStar bought them, you know, Comcast bought them, and we sold them to TV stations. It's different now, actually. It's really, ATSC1 is really the last worldwide market that's still, you know, a decent sized market that's using MPEG-2 HD. You know, so it's different than it was then. ATSC1 also has the smallest StatMux pool size of any application that's commonly used. So the StatMux pool in a cable QAM is double the size. And the StatMux pool in a satellite transponder is usually triple the size or more. So that changes things, because you don't have enough programs in an ATSC to get constant quality. So the underlying theory behind StatMux was, you know, they taught us all this early on, is if you're in constant bit rate, you have variable picture quality. So the picture gets bad when there's a transition, but it gets really good when there's no motion. So you have variable quality. A good StatMux, you know, and especially with the original sort of concept, was if you have enough pictures, you average the bit needs across all the pictures, and basically you achieve constant quality. If I have a transition or a pan and I need bits for my particular program, I borrow them from the channels that have no motion. And so if you have a big pool and enough programs, you get to constant quality. ATSC1 is nowhere near big enough to do that, especially with HD. You can almost get there with SD, but even there, it's pretty limited. The other thing that's unique about ATSC1 is extreme prioritization, and it's the norm, it's not the exception. Many other applications do not ever use priorities in the StatMux because it's a bad business decision. So, you know, particularly if you're a satellite broadcaster or you're a cable programmer, and, you know, if I find out that I'm Fox Sports and you've given ESPN more priority than me, it's not going to be a pretty picture. So again, ATSC is one of the few markets actually that uses priorities. And it doesn't just use priorities, they're used in the extreme, you know, where you want huge differences in picture quality from one program to another. Pools with HD and SD in the same pool are not common at all. So if you go to a cable company, you usually find, you know, they have all HDs or they have all SDs in a given pool. Satellite tends to do the same thing, not always, but the mixture of HD and SD in ATSC tends to be pretty unique. And then finally, you know, what you want is so different between HD and SD. So, and the programming is very different. So, you know, the typical SD channel now is a mixture of film and tape, and the program is 30 years old or more. You know, there's a, you know, as opposed to the HD, where it might be a sporting event and, you know, the whole production was done in ultra high definition and then down converted. So it's the ultimate clean source. So, you know, they're way different that way. We intentionally starve the SD channels. I mean, you know, anybody with a TV station who's carrying the pass-through channels, basically, you know, you make them look, you make them watchable, but you're not going to sacrifice football for them. So that's one of those areas where constant picture quality, but modest constant picture quality is what you want, as opposed to striving for the best picture quality at any given instant. And then the HD content, again, you know, it's very clean sources. But then you have prime time, which is usually shot at film rates. It's usually shot with video cameras now, but they're usually running 24 frames per second. You know, it has 3:2 pull down on it, but the cadence is disrupted every time there's a commercial or something. So again, those are all things that make ATSC1 a little unique. So just, you know, sort of summing it up, you know, the 1.0 density is now somewhere between 2 and 4 times what it was in, say, you know, 97 or 98. I mean, it's a remarkable difference in the efficiency of the encoder. There's still room to improve MPEG-2. And SD, like I said before, is about 7 to 10%. And really what I've learned, so if you go to most engineers at Harmonic who deal with other markets and you say, well, it's, you know, is this, how much more efficient is this encoder than that? What they'll do is they will put the two side by side. They'll, you know, turn down the rate on one on the better one until it equals the poorer one. And then they'll say, oh, well, you know, I turned it down 10%. So it's, you know, the better one's 10% more efficient. That actually doesn't work in ATSC. What I find now, especially, you know, that used to work. Nowadays, to me, the real measure of efficiency is, okay, here's the primary channel or channels that I have to do. How many SDs can you give me with that? I mean, that's the question. And to me, the efficiency of the encoder is you look at how many HDs you have and what the programming is, and then you measure how many SDs you can put with that at a quality that's acceptable. And, you know, that's the only real measure that is particularly meaningful. You know, adding more SD channels, it involves filters, StatMux, codec, all those things. Harmonic did a lot of work on this maybe a year or two ago, where we got content from, you know, some of the purveyors of pass-through channels, and we tuned the SDs to work better with it, to look better at lower bit rates. You know, all this stuff comes 1% at a time, though. And nowadays, I don't think you can be, you know, you can't get to the top tier of ATSC1 unless you do some specific tuning for ATSC1. It's just too different. MPEG-2 now is running actually quite a bit lower than what AVC was expected to run at when it first came out. And in fact, it is running lower than Harmonic's first generation of AVC encoding. I mean, it's significantly lower. AVC's improved at the same rate. It's, you know, typically about half the bit rate of MPEG-2, and it has been all along. It's just that they both get better together. ATSC1 may be able to support AVC. It's something that I actually have experimented with, usually on, I've got a few systems. They're basically PSIP-based internal cable systems. And some of those run AVC channels. And so you get to find out how many TVs work with them. And really the majority of TVs could display AVC pictures. So that's a possible, you know, that's a possible sort of next step when we get to that light or the night light situation where there just isn't enough room. Just a, you know, sort of an observation and really a recommendation. You can't test with, you know, with stock tapes anymore. You've got to test with the actual content. It's just, it's to the point now where, you're doing so much to the picture that different content, even if it's, football versus soccer, or, or even, different kinds of sports, that sort of thing. One doesn't predict the other. So you have to, when you test, you have to test with actual content. And in fact, that's what we do. I mean, we collect content. I mean, some of you that know me are know that I ask for content because, we're always looking for it. MPEG 2 is going to be really old by the time it's retired. I mean, I'm thinking that we're not going to get rid of ATSC 1 completely until probably 2037, something like that. Maybe a little earlier if things go really, really well, but I think it's going to be around for a very long time. On the other hand, I still listen to AM radio every day. I get in the car, I turn it on, I want to know what the weather is, I want to know what the traffic is. AM radio still serves me, but I don't watch NTSC, so who's to say? And there are techniques that we gain from one application into ATSC 1 that sometimes make a big improvement. Sometimes something was thought of or financed by some other application, and we find that it's useful in ATSC 1. So there are still improvements coming from that. So why don't I open it up to questions? And if we have time at the end, I have maybe 3 slides of advertising, but they're not a requirement, and I'd rather take questions first.
You were talking about the need for real content testing. And as you were describing that, I was thinking of an experience I had working with one of the MPEG Layer 2 audio encoder manufacturers in the 80s. And our company was complaining about the inability of the encoder to work on a particular set of male voices.
Mm-hmm.
So we drove up to New Jersey and worked with the manufacturer. And as for background, he said, "Here, I want you to listen to something." And he pulls out their new encoder and played this classical music piece through it. He said, "How did that sound?" It was just, a 30-second clip. And it sounded fabulous. And I told him so.
Right.
And he said, "Okay, now listen to this." And he plays a piece from Simon and Garfunkel, Scarborough Fair, the simplest tune you could ever imagine. And it just totally destroyed the codec. It sounded dreadful.
That's right.
No changes in settings or anything. But so that really struck home for me.
Yeah.
Content does make a difference.
I have some content that is, for practical purposes, unencodable. I don't usually use it to test quality. What I use it to test is, can you actually break the encoder? So and I look for content like that, and Harmonic is always looking for content, and good content is great, but bad content is even more important. Other thoughts, questions? Surely there must be someone.
Yeah, surely there's some out there. Don't forget, everybody, you're probably on mute. So if you have your question, go ahead and take yourself off mute.
Q. Dave Burke with Gray.
Hi, David.
Hey, Michael. Thank you for doing this. It's very nice presentation, very extensive. Back when you talked about some of the challenges of the StatBux pooling with ATSC 1.0 versus other mediums, do you see any marked difference if you mix 1080i with 720p? Any thoughts on that?
So, everybody used to talk about how much better 720p was to encode than 1080i. The difference is less than it used to be. And no, there's no particular advantage to, a mix versus not a mix. I mean, 1080i has more pixels that you got to encode. My observation has been that native 720p content, so ABC or Fox content, is easier than, say, CBS content, which is native 1080i. But if you take 1080i content and down convert it or cross-convert it to 720p, there's really no advantage left with most content. Some content there is, other content it actually looks worse. And mostly it has to do with, you reduce the pixel count, but you add a lot of edge noise that, from the deinterlacing. And so I find that there's not a huge advantage there. In terms of mixing pools, it really doesn't make any difference. I mean, you can do PAL rate and NTSC rate simultaneously on our encoders. They don't really care because it's not frame based. It's time based. So they don't have to be synchronized. It doesn't really care whether one's 60 and one's 30. If you want to try and do 3 HDs and you've got a network that requires that you do 1080i, you leave it at 1080i, and as long as you got a 720p in there, you can probably do 2 1080is. At least it happens in some stations, mostly smaller markets. 3 720s is definitely easier than 3 1080s is a real stretch. But when you get into, dual and triple stations, yeah, with one's 1080i, if the primary channel is 1080i, it's definitely better if one or two of the others are 720p. So I don't see a huge advantage in, having them all one or the other.
Okay, I'm only asking a question because nobody else is asking questions.
Okay.
I just have to, personally, has working with encoders for decades made it difficult for you to watch television off air and enjoy it? Or do you always end up seeing the encoder?
It's funny. I started my career, my first career was, I was a recording studio chief engineer. So I spent a lot of time listening, in recording studios to good quality. And I very quickly learned at home that I just wanted to listen to the music. I didn't want to be distracted. So I couldn't have bad quality. I couldn't deal with bad quality, but it didn't have to be perfect. I find at home, my preference is to sit a little further from the screen maybe than is the optimal distance so that I don't see the artifacts because I don't want to see them. I notice them in Netflix, but I can usually, I'm usually okay with it now. Like I say, to me, the trick is, I don't want a huge TV. I want something that I can be, 4 or 5 picture heights away. I don't want to be 3.
Thank you.
Michael, do you find that there's an optimal mix of channels between HD and SD? I mean, is it better to have, a couple of HDs and a couple of SDs, or a single HD and multiple SDs, or does it matter in that type of a mix?
The best mix is the one that makes you the most money. But to sort of look at the science behind your question, HD per pixel is much more efficient to encode than SD is. It was not originally. Back in 2000, if you did the pixel count and then compared the rates, it was almost the same between HD and SD per pixel. HD content now is many, many fewer bits per pixel than SD is. On the other hand, if you have a huge number of SD channels, the StatMux works better. So, the answer to your question is complicated. It's content dependent, it's everything else. What I would say is, with a good encoder, you can do almost any mix you want, and if it's realistic, you figure out how to make the encoder do it. They're pretty good now at mixing those things up. It wasn't always the case, but we have you're using basically the same code for both, with the same look ahead, and they're timed really well together and all that, but they do encode very differently. So an HD, like I say, is much more efficient per pixel if you look at the HD rates as a multiple of the SD rates for the same quality. you'll find that HD encodes really a lot easier. On the other hand, when HD needs bits, it needs a lot of bits, when you have a transition or whatever. So it's, it's content dependent, and it's, and it's business dependent. I mean, what I say about ATSC now is it's not really a stat mux. It's allocating bits according to business rules. And that's really the goal. You're not trying to make every picture perfect. What you want is the appropriate quality for the channel so that you can fit as many channels in as you can. If you want every picture perfect, you can cut in half the number of channels.
Is there any way, Michael, that you could do a trade-off for it, a little bit more time, give the encoder time to do an extra pass to improve the quality, and say, you know what, instead of a 2 seconds of average delay for an HD, maybe I'll take 3 and see if I can gain myself a little bit more picture quality? Is that something that you guys are doing?
Well, we're up to about 4 now. So yeah, the length has grown over the years. There are limits to that. I mean, once it gets to a certain point, it's like, I mean, you could encode it offline, right, and spool it out. But there is right now, there's actually slack built into the timing of the encoder. I mean, there's actually extra room in there. We do things like remote stat mux, for example, where we have to adjust the timing of the pictures. If one encoder is 1,000 miles away, you have to delay. You have to have delay built in so that everything can get resynchronized. But if they could take another half second and improve the quality, they probably would do it. We're getting now to the point where some applications, not necessarily ATSC, but some applications are saying no, the latency is too long. So we're starting to have to put in lower latency modes. That's particularly true, for example, in South America, where you have multiple broadcasters carrying the same soccer game. No one wants to be the last one to show the goal. And it actually has been a problem. So, there's limits to how much you can gain with more time. If you can get more than the longest GOP you're going to make, for example, you're pretty much there.
With a typical network, CBS in my case, what do you think that sweet spot is, in your opinion, for a bit rate for that type of program?
To be really honest, I don't have an opinion on bit rates. I mean, I'll expand on that a little bit. A CBS owned and operated station is going to run HD at a much higher bit rate than, a small affiliate down in West Texas, right? When you get to West Texas, I've put in, or, different places, but several places where, I've put in encoders in stations that were affiliated with 3 networks. I did a CBS, ABC, Fox combination with an SD, by the way, years ago. That was the Electra 8000, and you look at it and you say, well, boy, they're giving up some picture quality, but it wasn't bad. I mean, when I looked at the pictures, it'd be like, I watched that. And it meant that the viewers in that market had access to another network in HD that they wouldn't have otherwise. So the appropriate bit rate there is probably half of what it is in New York, where you've got, an owned and operated station, in the #1 market. So it really, the important thing to me is not trying to peg a bit rate on it, but trying to find picture quality that's appropriate to the business case and the programming. And, and to the viewer. Nobody likes to put out bad pictures, right? but there is an appropriate quality. Like a PBS station is a great example. If you're doing distance learning, the SDs can be incredibly low because there's not much motion, and if he waves his hand, or is writing on the chalkboard and there's a few blocks around his hand, it doesn't take away from the program. Like I say, I try not to have an opinion on that because it's just so specific to the application. CBS, I worked in the lab with CBS you know, before they purchase their encoders. And we spend a lot of time, you know, figuring out the best combination to their eyes, not to my eyes. You know, because my eyes are not, they're not the ones that matter. So that's a very non-committal answer, I realize, but it really is. I don't like to tell people what is good enough or not good enough. When somebody asks how many bits do I need for this, typically the answer I'll give is some examples of stations that are doing what they're asking about. Because that's, to me, the criteria is if you put in an encoder with a certain channel count and they still have the same channel count a year later, you know, it's probably okay. If they add a channel a year later, you know, you could have done a little more, right? Does that make sense?
Yeah, absolutely. Thanks.
You know, I mean, you know, I'm very impressed with CBS's commitment to quality, by the way. You know, I think they leave money on the table, you know, to my eye, but maybe not. I mean, you know, it's a successful network. You know, who am I to judge that, right? You know, you do what makes you the most money, and everybody has a different idea of that.
A question about stat muxing. I've got some fairly small stat muxes of 3 channels, and occasionally the editorial staff decides they want to simulcast an event, and it puts a kind of strain on the stat mux when you have two out of 3 or all 3 pictures with identical material. Would I benefit by delaying, adding some sort of delay and if between the video sources? Some sort of fixed delay upstream?
Oh,
So,
absolutely. Absolutely. You know, at 1 second, you gain back most of the efficiency. At 3 seconds, it's a different program for the most part. So yes, if you can put a second of delay in there or second and a half, something like that, it will make a big difference. I mean, just think about transitions, which are difficult. You know, if you know, with 1 second in there, the encoder has plenty of time to move the bits around to make, you know, to give them all what they need. So yeah, absolutely, you want to put a delay on it.
Michael, have you seen any particular mixes of HD and SD? I know that it's not necessarily putting you on the spot for a bit rate, but just a mix of HD and SDs that you would consider mainstream using the Harmonic.
So the way I usually answer that question is I consider mainstream to be what people are doing successfully in maybe the top 20 DMAs, something like that. You know, if you look at ABC, for example, their owned and operated stations, most of them are doing 2 HDs and an SD, and they have for a very long time. I mean, across what, 3 generations of harmonic encoders, and I think it looks good. You know, I've demonstrated, you know, 3 HDs in that combination, you know, with a lot of prioritization, mind you, you know, but you know, so I think 3 720p's can absolutely be mainstream. If you take away a 720p, you can pretty easily replace it with 2 or 3 SDs, something like that. NBC in New York has a channel share between NBC and Telemundo. You know, right now it's 2 1080i's and 4 SDs. Is it perfect? No, I don't think they get a lot of complaints, so I'm not aware of it. So, you know, some of these aggressive combinations are pretty mainstream now. Some of the channel shares that I was involved with, you know, are pretty aggressive. You know, 2 HDs and you know, 4 or 5 SDs. But again, it depends on your tolerance. You know, it's to put it this way, to my way of thinking, if the picture looks bad all the time, it's just bad, right? Once you get to a certain point where you occasionally see things that you don't particularly like, but it's occasional. And the real quality judgment then, and that's because it's not really statistical, right? If you've only got 3 pictures or, you know, 3 HDs, in a stat mux. It's not really a stat mux, right? They're sharing bits, but it's not very statistical, if you know what I'm saying. So at that point, what happens is the stat mux is reducing how many times you see that, but it's not making it impossible because you don't have enough pictures for the stats to work. So, you know, at that point, personally, my judgment is, well, how often am I really seeing that? You know, if you see a few fleeting artifacts every now and then, I'm not offended by that, but you may be. So again, it's a roundabout answer. I don't, you know, it's so hard for me to tell people what, you know, how many bits is enough. It's the most difficult question. Actually, it's not the most difficult question. The most difficult question was at NAB, somebody brought their attorney and asked me to explain StatMux to him. That was the most difficult.
Oh, no.
Anybody else? Any thoughts?
Well, Michael, what is Harmonic doing? I mean, I know you said that you're getting periodic, you know, 1% here and there. Is that something that, you know, in the last year, can you quantify that and say, hey, a year ago, our version of our X2S or XOS was, you know, here, but we're 3% more efficient today than we were a year ago? Or
again, it's a very qualitative thing, but I think that the stuff that we did with SD channels about a year and a half ago, it came in and it came in little pieces. It wasn't all at once, right? But the code running now on an X2S versus say 2 or 3 years ago is, in my opinion, more than one SD. It may or may not be 2 SDs. It depends on the mix of content, that sort of thing, you know, and what you're willing to do. But it's, you know, I think we've gained certainly, I think, a full SD. And since the product was launched, I think we probably gained 2 or 2.5 SDs. But again, you know, your mileage varies because it's, you know, SDs are not all the same, right? And like I say, I tend to measure efficiency in SD channels because it's, you know, if you make a 3%, if you make a 7% improvement in an encoder and look at the same program mix, you probably won't see the difference. But if you can take and do a 7% increase and throw another SD channel in there and say, gee, the HD still looks the same, that's a genuine 7%, right? So again, it's really hard to say. It gets better all the time. I mean, every release typically has something in it. It may not be specific to ATSC. I mean, it may be something that was developed totally elsewhere, like some of the filter algorithms, for example, get better because, you know, because it was developed for, you know, HEVC or something, you know, and, you know, and then, you know, there's, you know, the ATSC comes around and, you know, we get, you know, engineering and marketing fulfills some of our wishes and, you know, maybe we'll, you know, maybe we'll get a couple of percent. But it's a slow but continuous process, you know, and, you know, it's always been that way, actually. You know, that there was really, I think the only real quantum leap, you know, in terms of like from one generation to the next was when the Electra 8000 came out and we came from the sliced encoder to the single slice, the full frame encoder. That was huge. That's probably the only time I've ever seen like a night and day difference. I hope that answers your question.
yes, thank you, Michael.
Michael, do you want, I'm sorry, is there another question?
Just one last one on HEVC encoding for UHD. Are those all full slice encoders, or do you expect a big jump?
No, they're all full. They're all single slice. They're all single slice. You know, you don't get many per Xeon. Let me put it that way. It's a lot of work. But of course that's the advantage in CPU encoding is it's not tied to a chipset. It's you know, for UHD, well, you just throw the whole server at it. if you have to.
Okay,
So yeah, they're
thanks.
single slice. They have look ahead. They have all the features, but the density is much lower because you're throwing a lot of CPU at it. You know, I mean, one of the things I told the engineers actually is there are TV stations that if we only got 2 channels per per chassis, but they were a whole lot better. There are TV stations that pay the price. You know, it's but that's the huge advantage in CPU is you just throw more CPU at it.
Michael, you mentioned that some ATSC1 televisions you think can support AVC. I'm curious if how you expect or anticipate that might play out as we move toward ATSC 3.0. Do you see that being a useful tool in our toolbox for the transition?
I do. I think somebody has to experiment with it. There's been some experiments with it. I was terribly disappointed that ATSC 2, if you remember that, did not, just provide AVC for the main channels. My thinking at the time was, well, you can require MPEG-2 on the primary channel, but you should be able to add as many AVC channels as you want. And I don't think there's anything illegal about it. But in my experience, if you take new televisions, virtually all TVs made in the last 5 years probably support AVC, no problem at all. Earlier ones, if they were a smart TV with Netflix and that sort of stuff on it, most of them did. I've got a facility where I did one of these ATSC-based cable systems, where we use QAM modulation because the TVs can all demod it, but we use PSIP, so you don't need a set-top box. This is a broadcaster, and they had, I think, I don't know, 3,000 TVs, something like that. And every now and then we wouldn't have a transcoder available and we'd throw up a channel in AVC, and there, out of 3,000 TVs, maybe there'd be 100 that didn't work, something like that. So it's pretty good.
Well, and with your 7-year average for televisions, 5 years now means just a couple of years out, we're going to see a pretty good size, an even bigger number.
Yeah.
So
yeah,
interesting. Thank you.
I think it could make the transition a lot smoother if it became common practice and if there was a way to sort of tell people what's going on when it doesn't work, Anybody else?
Michael, I wanted to give you the opportunity to show your remaining slides that were.
Okay, I will.
Commercials.
I promise no more than about a minute because I don't like these things to be commercial. So let me just touch on a couple of things and then I'll be done. Let's see, it helps if I get there we go. So the latest solution is really an ATSC 3 solution. It will become an ATSC 1 solution sometime this year, but right now it's primarily aimed at ATSC 3, and that's called the XOS. It is much more than an encoder. It does a lot of things. We can actually even put an L-band card in the front end, so you can have SDI or IP or L-band coming into it, 2110. So there's lots of things like that. It'll put out transport streams with StatMux. It'll put out package stuff and all that. So it's going to become a very sort of broad product that is kind of modular, that you can do almost anything you want with. And it is all software. It's a single chassis sort of thing. In a lighthouse, it's the if you build a lighthouse, it's the primary solution that we would normally offer. But for example, in X2S, nearly all X2S installations can feed a lighthouse with a 1080p without running out of CPU power. There's a few of them that we've put 3 or 4 TV stations on that might be stressed, but in most cases in X2S you just add an AVC or an HEVC to it to feed 1080p. If you want UHD, you do need the XOS. So, and then there's, of course, the one that everybody knows, which is the X2S, which is, I think it's the largest selling ATSC encoder. It's certainly the largest selling one we've ever had. And to tell you the truth, it surprised Harmonic. Harmonic did not expect that. It was put together because of the Spectrum auction. And, you know, we were all hammering on marketing and engineering that we had to have something like a lot better than what we had at the time, which was the 9200. And so the X2S was a result of that. And then sort of at the same time, the Diginets started really driving encoder purchases. And so it's really taken off and been a good product for us. And that's the advertisement.
Did anybody think of new questions while they had a minute to?
Got as much time as you want.
Well, I noticed we've lost a percentage of our audience, but we still have about 3/4 of it, which is usually pretty good for this point in the presentations. And I think we peaked out in the mid 40s, which is pretty good when you have 72 signups, because we usually get about, I'd say, 2/3. So a good meeting. We have not locked in our meeting for next month, but keep an eye on the website, and we'll certainly send out email blasts when we lock down the program. And with a bit of luck, hopefully we're working our way towards being able to see each other again in person. I just got a text while we were sitting here from my 84-year-old father in St. Louis that he got his first vaccine today. So hopefully we'll get to see all of our parents and friends and very soon.
And each other.
And
Michael,
each other.
Michael, thank you so much.
I'm honored to be invited. I thank you guys for coming out to hear me.
It was very practical, by the way. Really do appreciate you. There was something here for everybody, tech heads and Pete, just regular broadcasters. So thank you.
Thank you, guys.
Yeah, and a thanks to VTS for sponsoring the webpage and the meeting. And earlier this year, we did have BGS as a sponsor, so we don't want to forget them too for helping us get through this crazy time.
Good night, everybody.
All right, I'm going to stop the recording. It'll be available at some point. Thanks, everyone.
Thank you so much.
Thank you, everybody.
Thank you all. Good night.
Thank you.